The next topic we're going to cover has to do with sequential streams, which is what we've looked at primarily thus far, and something called parallel streams, which is a very powerful, very convenient way to optimize Java streams processing to work effectively on modern multi-core processors. So we'll talk about what sequential and parallel streams are briefly, and then I'll give you just a kind of high-level warning about some of the hazards that can arise when you use parallel streams and don't quite understand what you're doing. So we'll basically have a word to the wise up front to make your life easier when you start getting into the details of parallelizing things. So by default, stream operations run sequentially. In other words, there's one thread of control, and all the processing, all the aggregate operations, the behaviors that are applied, and so on and so forth, they all take place in one thread, which is at any given point in time mapped to one core. As if a program runs for a long time, through the magic of time slicing, the thread might actually get mapped to different cores, but from the point of view of the logical concurrent behavior of the system, there's only one thread, and it's running sequentially. You can also, with very little effort, convert a sequential stream to run as a so-called parallel stream, where all of a sudden you can have multiple threads. In fact, there's a pool of threads that do the processing, something called the common fork join pool that we'll cover later. And those threads in the pool get mapped to the underlying cores. So if you have 4 cores, which is pretty common these days, you'll typically have a pool with around 4 threads or so. And we'll talk later about ways to control the number of threads that are allocated relative to the number of cores. But from the first order approximation here, we don't have to worry about that. We don't know or care how that mapping works. We just know that things are going to run more efficiently, especially if you have so-called embarrassingly parallel programs where there's no dependencies between the tasks that are running. The way this works under the hood is it also applies the split, apply, combine paradigm that we talked about with those 3 phases. And a parallel stream will split its element up into multiple chunks by using something called a splitterator. So when you take a look at the assignments 1B and 2A, you'll see there are these splitterators, and their purpose in life is to help with splitteration and with parallel streams and so on. And then after things are split in the split phase with a splitterator, then the little chunks that are created are going to be applied in the common fork join pool to run in parallel. So all the elements that are split up will then get a chance to run in parallel in the pool of threads. And then it may come as no surprise that there's also a third and final phase, which is essentially the combined phase, where the elements that have been running in parallel are then joined back together again to give a final so-called reduced result. And we'll talk a lot more about that as we get later on in the course. But that's the basic idea here. Split, apply, combine, and you can do these things in multiple threads. One of the great things about a parallel stream is it can often be much, much more efficient and much, much more scalable than a sequential stream without having to do much additional work. So here's a very simple example on an older computer that I had that has quad core, 4 hyper-threaded cores, so effectively sort of 8 virtual cores, running with 32 gigabytes of RAM. And as you can see here, the sequential version took about 2,000 milliseconds to process. And when I ran it with a highly optimized parallel version, which we'll look at later, it executed in about 400 milliseconds. So a very nice speed up. And the reason why we got such a good speed up was, number 1, Java Streams is very efficient with respect to parallelization. And also, number 2, this problem is inherently embarrassingly parallel. So there's really no dependencies between the different elements, and everything just scales up nicely. My computer I'm running on right now has 8 cores, and you get basically an eightfold speed up or so with the 8-core version. So it's great. You get pretty much linear speed up. But of course, things are not always unicorns and rainbows, as I like to say. And so there's some common hazards when you program with parallel streams. We're not going to cover these in great detail at the moment. I just want to alert you to the fact that they exist. And then when we get to the right point in the class later, after we've covered sequential streams in more detail, I'll introduce this issue with more depth. So ideally, you would like the behaviors, those method references and lambda expressions that are passed as behavior parameters, as these methods to the aggregate operations, you'd like them to depend only on the input arguments. So a fancy way of saying that is that there should be no side effects. That's just a kind of the way that we talk about this. And that just means that you're not going to be storing state in a collection. You're not going to be storing state into a file. You're not going to be sharing anything between different cores and different threads. It's all kind of self-contained, in and out, parameters and return values only. Here's a very, very simple example, but a good example of a method that has no side effects. So you can see here we pass string s to the capitalized method, and what it does is if their length is 0, it just returns the string, which has nothing in it. Otherwise, it takes the first element in the string and uppercases it, makes a substring that's uppercased, and then takes all the other elements and goes ahead and lowercases them. And you can see that the result that comes back here is just the modified string, if it wasn't already capitalized, that is. And in either case, there's no side effects other than taking parameter or parameters, performing a computation, and returning a result. There's no other things. We're not storing anything in a collection, storing anything in a file. So as a result, we don't have to worry about other kinds of hazards. What kinds of hazards might there be, you ask? Well, the most common type of example are so-called race conditions. And this won't really bite you if you limit yourself to sequential programming, because there's only one thread of control. But as soon as you have parallel computation, as soon as you have a pool of threads that are working on some elements that are shared, then you can have so-called race conditions. And race conditions are very frustrating. They're subtle. They're pernicious. They tend to do bad things at the most inopportune time, like when you're doing a customer demo or you're trying to control the speed of the airframe and keep it on course, or you're trying to measure the temperature of the nuclear reactor, prevent it from melting down. Inevitably, race conditions will occur at the worst possible time, kind of like Murphy's Law. So what is a race condition? Well, a race condition is a problem that arises when your software or your application, based on software, depends on the sequence or timing of multiple threads in order for it to operate properly. So race conditions occur if there are shared mutable state that can be accessed, read and written, loaded and stored, if you will, from multiple threads, and you only get the right answer if things happen to go perfectly. And of course, in practice, things never go perfectly. Things operate and run non-deterministically. That's kind of the whole point of concurrency and parallelism. And so inevitably, you'll end up with one thread trying to modify an object or a field that's also being accessed or modified by another thread. And since they end up occupying the same space in memory, the results will have non-deterministic and very erroneous and weird results. So I like to think about this. The mental model I think of when I think of a race condition are two cars trying to occupy the same space on a road. And of course, you can see from the diagram here what happens. You have a collision and there's damage and it's just bad. So race conditions are the root of all evil in concurrent and parallel programs. There are other kinds of problems as well. Race conditions are not the only problem, but they're a good starting point to kind of get comfortable with the concept that things can go wrong. Here's a very simple example to illustrate the concept of race conditions in parallel streams. So as you can see here, we have a factorial method. This is in my EX16 folder in my GitHub repository, so you can try this out and run it yourself on a multi-core machine and see what weird side effects you get. So what we're trying to do is we're trying to compute the nth factorial in parallel. That's what we think we're doing. What we're actually doing is we're making a big mess. And the reason we're making a big mess is that we're allocating an object, which is an instance of this hidden class called total. And this object, which looks innocent enough, actually has shared mutable state, which is the root of all evil in concurrent and parallel programs. And what we mean by this is if you take a look, you can see that there's a field called mtotal of type long, which gets initialized to 1. And there's a method called mult, for multiply, that's going to do the multiplication and update, the times equal operation, which is going to multiply total by n and store back into total. So it's several steps in an instruction sequence, it's going to do that. And this will work innocently enough if there's only one thread of control. But the moment we start running this with parallel threads of control, which is what we're doing here by using a stream of numbers from 1 to n, and then running computations in parallel, what you can see in this particular case is we're going to go ahead and have mult be called by multiple threads at the same time, modifying the value of m total. And so again, this would work perfectly fine if there's only one thread of control, but when there's multiple threads of control, those multiple threads are going to be updating and reading m total at the same time. And since mult is not defined as a synchronized method, there's no synchronized statement, there's no synchronizers there, the multiplications and updates are going to be interleaved, and believe me, you will get really, really weird results. So if you need to prove that to yourself, try running the example and you'll see it's like really strange behavior. So this is a good way not to do things correctly. So that's an example of race conditions where the modifications take place simultaneously and the operations interleave and bad things happen because we haven't properly synchronized the code or made it so there's no dependencies between the various elements. There are other problems here as well. There's also issues having to do with memory inconsistencies between processor core caches. I won't spend a lot of time on that topic right now. If you're curious about that, please take my concurrent object-oriented programming class where we'll spend a lot of time on atomic operations, and you'll see that memory inconsistencies and race conditions and deadlocks are some of the common problems we run into when you start trying to do concurrent and parallel code. But be that as it may, this is a problem. Moreover, only you can prevent these types of concurrency and parallelism hazards. So the compiler won't save you, the Java execution environment, the JVM, for example, won't save you. You can be saved if you're willing to use some sophisticated tools like static and dynamic checkers, various kinds of memory access checkers, sort of the concurrent version of Valgrind, if you're familiar with that. But the long and the short of it is you're just better off being able to write proper code in the first place and avoid this incorrect sharing of mutable state, which is the root of all evil. So that's a quick overview of sequential versus parallel streams. We will cover this in a lot more detail later in the course, but I just want to kind of sensitize you to the issues. And by the time we get there, since we'll have been focusing on doing sequential programs that don't have side effects, then it becomes trivial to switch from sequential to parallel, get a big speed boost, and not have to worry about these hazards that we just talked about.